بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على سيدنا محمد وعلى آله وصحبه أجمعين. نبدأ بعون الله تعالى المحاضرة الثانية من ورشة العمل هذه. طبعا إن شاء الله بنغير بين اللغة الإنجليزية والعربية، وهي طبعا الورشة أصلا مصممة للطلاب، لكن في بعض الموظفين ربما من بعض شركات النفط أو شركات أخرى منضم إليها. السلام عليكم ورحمة الله. طبعا في الجزئية الأولى we started with lecture number 1 and we've done overview of the petroleum system of Oman. Unfortunately, we couldn't cover the full slide package. However, we've gone through most of them, so I'm going to just complete on these, and then after that I'll start to explain about lecture number 2. So lecture number 1 is overview of the petroleum system, and then lecture number 2 on the geophysical data and seismic interpretation workflow. And I'll give you an introduction about Petrel, something we've missed last time we met. So last time we went through the sedimentary system, and we've said that for carbonate, for instance, the story is quite complex in terms of facies, the types of rocks, because you have very good quality rocks and then you have poor quality rocks, and between these you have spectrum of recovery. And for most petroleum reservoirs, the recovery, the gap between the oil in place, the amount of oil that the tank or the reservoir stores versus the recovery, our extraction of oil from that reservoir is big. And there are a number of good examples of that. This is one of the biggest fields in Oman, and you can see there is, despite producing this field now for almost 50 years or so, we still haven't produced, or we only produced around 25% or 30% of this reservoir. Whereas for sandstone or clastic reservoirs, the story is different. The story is more of how to find the channels that have the oil or store the oil. And that usually has different type of complexity. But then when you find the sand, usually the porosity and permeability is not that big issue. Then we spoke about Oman, evolution of Oman through time, and I said that one of the key messages you need to remember from the previous lecture was to actually remember that during the Cretaceous time, Oman was subjected to a northwest-southeast compressional event, which produced strike slip and normal faults, transtensional, that's what we call transtensional faults. And that these emphasis of this or signs of this we can see all over Oman from north to south. And then during the tertiary time, the whole system was kind of inverted. And the reason for that, as you know, is the collision between Arabia and Eurasia, and therefore the formation or the onset of a northeast southwest tectonic regime. And Abdul Munaim will share with you the Dropbox link, in which there is a paper we published in 2014 that speaks about these events, and there are also other papers that thoroughly have gone through such tectonic events. We spoke about then some of the petroleum system elements in Oman. And then we started to speak about the main reservoirs. We said we have dolomite as reservoirs that go back all the way to the Precambrian time. And then we spoke about sandstone reservoir that are mainly in the Paleozoic, اللي هي بالعربي حقبة الحياة القديمة. And then we have reservoirs mainly limestone in the Mesozoic, حقبة الحياة المتوسطة. Okay, and then we said we have also seals that are going through different times. And then we have also different types of traps اللي هي بالعربي المصيدة والسيل اللي هو السدادة. And then وبعدين عندنا different types of source rocks. So we have different types of source rocks that span time from Precambrian up to 600 million years ago or so to quite recent, as we see from the Natih source rocks. And we said that last time the geothermal gradient is very important to figure out whether a certain source rock has over time reached maturity, so therefore it expelled oil, produced oil. And we can see from here, we can measure from the styrene content, the percentage of C27 in the oil versus the isotope volume for various oils. We can find different signatures of oil. And the main oil families in Oman are the hook of oil, where 80 to 85% of oil from Oman comes from these rocks, the old rocks. We said that Oman in general have the oldest, among the oldest source rocks in the world. And we said that Mesozoic oil, which is here, comes usually have high values of carbon isotopes, and therefore they quite straightforward, not always, but quite straightforward to figure out whenever there is elements or traces of oil found. And we spoke about plays, and we said a play in petroleum terminology is this system or petroleum system where all the ingredients of a working petroleum system, a successful petroleum system, are kind of working or successful. And therefore, we know that there is oil. It's just a matter of finding the proper trap, okay, المصيدة, so that we just drill and find oil. And there are a number of play systems in Oman, and among the most famous ones is the Natih one. And the Natih one is the oldest that has been produced in Oman. We have the Shuaiba, Ghaba, and Eastern Flank, and the Eastern Flank is here. And last time we said we have the South Oman Salt Basin, we have the Ghaba Salt Basin, and we have the the Fahoud Salt Basins, 3 main salt basins. And most of the oil fields in Oman are either within these salt basins or on their boundaries. Apart from this, what's so-called Lakhwer area, we have fragmented fields here, heavily fragmented because of faulting, that are positioned outside the salt basins. And by the way, salt basins, they have huge control on the architecture of petroleum fields, because their deformation over time kind of define the complexity of the reservoir. And in many cases, salt tends to localize deformation. So we have in a single linear area or specific areas, we have a lot of deformations, a lot of faults, and so forth. Okay, and we spoke about the Natih play, and we said that the Natih play, a lot of the oil from the Natih play comes from Natih B source rocks, okay, or Natih E source rocks, so within the Natih formation, whereas part of it also comes from the hook of oil. So these are the 2 main source rocks within the Natih play. And the Natih play, we have 2 main fields that produce a lot of oil from this play, Fahoud and Natih, and we also have Dalil in there as well as a bit in Yibal, I think. And we said that the seal for the Natih formation is the Fika, which we can see in this stratigraphic column. You can see here, if we go back, that the Fika formation is actually sealing the Natih formation. It's a very thick shale that comes on top of the Natih. Okay, ladies and gents. So we saw last time that the Natih continues all over Oman, actually. So the transgression event that produced the Natih package of carbonate has covered the whole of Oman, more or less. Probably only a few places in Lakhwer, either it hasn't been deposited, or most likely it was not. It was eroded later on. But the Natih covers most of Oman, and then there are places in the Oman mountains as well where Natih formation has been eroded, most likely. So we have the Fika in this case sitting on top of the Shuaiba directly, or in some places on top of Narumar. So what we have here is source rock of Natih. So these dark blue colors, they cover north and central Oman, and then in South Oman, these wells are from South Oman. You can see the cross section here. these source rocks are missing, and you can see that the Natih becomes very thick. So in some places it's close to 500 meters of thickness, especially in places in central Oman. And then we have 7 members, A to G, and most of these are reservoirs with some mudstone or marl in between. And we said that the Natih is exposed, well exposed in a number of places in Oman. We said in Adam, near Adam, we have a place there called Salah Ark, the best place probably to study the Natih outcrops. We said in Jebel Akhdar Massif, or the chain of mountains there, you can see many transects, many wadis that expose beautifully the Natih formation. And we said the Natih in overall is usually heavily fractured, and most of the open fracture systems within the Natih formation are tending northeast, southwest. And by the way, in many cases, most of the open fractures throughout Oman are trending northeast, southwest. That's not to say that other fracture sets cannot be open, but it's more likely that to have fractures open in the northeast, southwest direction than in other orientations. And one of the main reasons for that is that because we have the current in situ stress in Oman is trending northeast, southwest, and that imposes kind of compressional stress on the tips of the fractures, yielding or leading to the fracture to open up, basically. And we can see loads of fractures in carbonates, the carbonates of the Natih formation. I will skip these few slides. We've covered them, and we said about viscosity. So viscosity is basically measurement. You can think of it this way: is a measurement of how easy the oil will pour. يعني in Arabic it will be كيف البترول بينسكب، سهولة انسكاب البترول مثل العسل. يعني بعض أنواع العسل يكون سميك، بعض أو ثخين خلينا نقول، وبعض أنواع العسل يكون خفيف. هي اللزوجة أو الميوعة خلينا نقول إذا ترجمناها بالعربي. It's a measurement of how oil would flow basically, and that measurement, the higher it goes, the heavier the oil is. Whereas API is the other way around. So API is measurement, American Petroleum Institute measurement of oil gravity. The higher it goes, the lighter the oil is. So you can see here that the light oil, which have low values of centipoise, they correspond to higher values of API. And API, you can think of it this way: anything less than 10 will sink more or less in oil, say in water, whereas anything above 10, I think it will float on top of water. That's why we have oil usually on top of water in reservoirs. And then here, measurement of depth, and obviously the deeper the rocks are, the more complex their facies tend to be, because they get subject to a lot of changes over geological time. And we said here, this is vitrinite reflectance estimate. And last time I didn't explain this very well. It was I had to do it very quickly. Anyway, vitrinite is just one of these components. I try to make it very basic. It's one of the components within organic matter, okay? And so it's especially coal, and it's almost an ingredient or part of the kerogen. Kerogen is the mixture of organic matter. And vitrinite is very nice in the sense that it has reflectance, and that reflectance usually can be used as a proxy or indication for the maturity, for how much of temperature the rock has been subjected at. So by measuring that reflectance, okay, and knowing when that reflectance was optimum, was highest, we can tell when the rock has reached its the temperature appropriate to expel oil. So from there, from this graph, we can say when was the oil of the Natih formation, for instance, was expelling oil. So for instance, here you would see that the oil generation rate was maximum some 10 million years ago. But however, it was active since 75 million years ago until present. So up to now, there are some places where oil is still being produced or expelling, coming out from the Natih formation. Biodegradation is, by the way, is when we have, degradation of the oil quality, usually by biogenic, processes, bacteria and others, and these cause oil to get heavier over time. And obviously they're related as well to tectonic history. So we said that a lot of the oil in the Natih formation is still not produced, and one of the main reasons for that is that because the reservoir in carbonate especially tends to be very complex, not only because of facies, a type of rocks, but also because of fracturing and faulting, because carbonates tend to be more prone to be fractured and faulted. And then we get to the Shuaiba play. Shuaiba play is also very complex. Now, in Shuaiba play, I think I can fairly or comfortably say that the main issue in the Shuaiba reservoir is not actually fractures, although they can be heavily fractured as well. But the main issue is facies, because Shuaiba, unlike the Natih is kind of consistent in terms of facies, at least within the Fahud and Natih fields. But Shuaiba is highly variable in terms of facies. You have very good type of facies like grainstone, where the reservoir quality tends to be good, permeability tends to be good, porosity is good. And then you go to something called, for instance, Lithocodium bacchinella, which is type of algae, mudstone and waxstone, whereby the facies are really poor and you cannot extract proper amount of oil from these rocks. And you can see that we have loads of fields that produce oil from Shuaiba, and we have large fields that store a lot of oil in Shuaiba, like the Khwer area here, loads of fields there. We have the Yibal, we have a bit of oil in Shuaiba and Fahud, and maybe very little amount as well in Natih. And then we have loads of fields in central Oman. This is what's so-called Qarn Alam area, where you have a lot of oil being stored within the within the Shuaiba reservoirs. A lot of complexity. This is a very nice transects that have been produced through the made across the Shuaiba, kind of bioherms or buildups, as well as what we call clinoforms. So clinoforms are these things. You can think of them as carbonate cycles that stack on top of each other. They can be formed at different stages during transgression or regression events. And these clinoforms, they usually are working petroleum systems. So you have reservoirs, and then usually below it and on top of it you have different types of seals. You have very good what do you call it, grainstone, so the orange color here. Sometimes you have this green color, which is not as good reservoir, waxstone, packstone, and then you have the pink, and pink is poor reservoir. In fact, in most cases it's not even a reservoir, and therefore we exclude it when we measure the STOIP. And so Shuaiba, you can see it highly varies. But look at the scale here. It's 50 kilometers, so it covers a huge part of Oman, from Qarn Alam all the way to the Khwer area. You can see a huge variability of facies in the Shuaiba formation. And therefore, because of that, you need to study the facies in the Shuaiba in order to be able to produce it well. This is a bit, I'll try to make it simple so that you receive it, you remember it. This is just a comparison of permeability measured from core data, okay? And this is porosity. So permeability against porosity. What you see here is that usually for clastic reservoirs, this relationship is more or less linear, and it's quite consistent. However, for carbonate, it is not, So for sandstone, the deeper you go, the poorer permeability becomes and porosity becomes. And usually higher porosity means higher permeability. However, in carbonate, it's not that straightforward. So you have 4 different curves here represented different types of facies. And for each curve, you get different porosity permeability relationships. So it's not always that when you have high porosity, okay, you get necessarily high permeability. So here, for instance, for this mud dominated fabric or facies, you get high porosity values up to 25% or between 20 and 25% porosity, but the permeability is still very low, okay? It's probably here, it will be less than 1 millidarcy or so. Whereas here for grainstone facies, when the rock quality is good, you can have small or low amount of porosity, low value of porosity, so 15% or 10%, whereas the permeability here is shooting up to maybe 10 or 100 millidarcy. So there is huge variability in permeability in relationship to porosity for various facies or rock types. And then when you go to saturation, also it's a bit complex for carbonates compared to plastic rocks. So for carbonates as well, the transition zone between water and oil can be very thick if the rock type is a poor reservoir, then usually have a big transition zone between oil. So there is a huge area between the oil-water contact and the maximum oil saturation, okay? A huge transitional area, and that area can be complex and it can store a lot of oil, which in many cases is very hard to actually produce. Unlike for plastic reservoirs where that transitional zone usually is not as complex. Shuaiba traps, we have huge domes. So in this case, in Qarn Alam, we have massive domes. Lukhwir is a massive dome. Okay, these domes, as Lukhwir, can be segmented sometimes by faults. In Dalil as well, heavily segmented by northwest, southeast faults. We have tilting as well. So by the way, in the Lukhwir area and other adjacent areas, the whole platform here, carbonate platform, was tilted during the tertiary time, okay, to the northeast by, let's say, degrees of about one degrees, okay, every I think kilometer. So that is, I can't remember. Actually, we made some research on this in the past, but I can't remember how many meters that is equivalent to. I would reckon maybe 8 meters or so every 10 kilometers. Or so. But don't quote me for this. It's just a number stored somewhere in my head. Okay. Anyways, so Shuaiba play, as I said, most of the oil in Shuaiba, especially in the Qarn Alam area, speaking about Qarn Alam area, here was expelled from reservoirs or generated from, sorry, not from reservoirs, from source rocks about 250 million years ago. And therefore, obviously, Shuaiba was not then deposited, you know. So the oil actually left the source rocks or was migrated from the source rocks, initially migrated from the source rocks 250 million years ago. However, Shuaiba was not then deposited actually, because Shuaiba is actually deposited in Cretaceous. So that won't make sense, isn't it? Because the oil left the source rocks before the Shuaiba was deposited on top. So how do we explain that? We explain that by saying that there was first a primary migration whereby the oil stored in what's so-called motile structures, and then there was another secondary migration from these motile structures to the Shuaiba. And that's important when you study the petroleum system of any area. You can see that for the Shuaiba, there is a huge spectrum, huge variation of gravity, API, and viscosity. So you go for fields like in Qarn Alam, where the centipoise of the viscosity measurement goes to more than 200 or around that range, to places like in Safa, where the oil is really very light, is less than 1 centipoise. So the API here ranges from 16 in Qarn Alam to around 42 in Safa and Yibal as well. And these are among the lightest oil you can find in Oman. And why is that? It's mainly because of biodegradation. It's also because of migration and remigration of oil in various parts of Oman. And therefore, we have different ratio between the gas and oil in these reservoirs, depending on mostly on the viscosity. The higher the viscosity is, centipoise, then we have lower GOR. Okay, so for Shuaiba play, a lot of development is usually needed, you know. So I'll give an example, for instance, especially for fields that have heavy oil, like perfect example of that is Qarn Alam in central Oman, where the oil is very heavy. However, the field is heavily fractured. So when the field is heavily fractured, okay, water flooding or water injection is not going to work, because you're going to bypass the oil by what's so-called recycling water within the reservoir. So what you use in this case, you inject gas, and in many cases that gas is steamed, so hot gas basically. So that's what we call thermally assisted gas oil gravity drainage, a complex term, but it's quite simple in terms of mechanics. So what you do is you inject gas on top, hot gas, and you try to make the gas work more or less. I'm not a reservoir engineer, so maybe Dr. Talar next week can explain this better if he's going to explain this mechanism. But anyway, the whole idea here is to use the gas as more or less like a piston as well, to force the oil move from the matrix towards the fractures, and then the oil will be pushed down through this fracture systems, and then will be produced from the lower part of the oil rim by what do you call it, emplacing wells at the lower part of the oil rim. And if it works in Qana Alam, it is working actually now. It shall really increase the recovery significantly from probably, I don't know, 3%, 4% in the last few years to above 20% or so, or around 20%. Garif play is, so by the way, Garif and Shuaiba are the largest plays in Oman. Sorry, did I say Garif? Garif and Shuaiba, yeah. Shuaiba in central and north Oman, and Garif in central and south Oman. And Garif is also a complex petroleum system. It has different types of complexities. So Garif is, by the way, divided to upper, middle, and lower Garif. Most of the reservoirs are within the upper and middle Garif. And you can see, and a lot of the oil which is within the Garif play is actually light oil. Unlike the ones on the eastern flank of Oman that goes all the way from Khizna in the north to Marmul in the south, or beyond Marmul, these are usually heavy oil. So for Garif, we have three types of what do you call it? Three members of the Garif. So the lower part is marine. I'll probably jump to this slide. I have a slide here. Yeah, this one. This one is quite good to explain. So you have upper Garif, usually channels, stacked channels, whereas in the middle Garif, in many cases you have, as well as these channels, you can also have sand sheets. Okay, that's quite common in the middle Garif as well as the lower Garif. So upper Garif, although it can be a very good reservoir, there is an issue there of continuity, and that continuity causes problems when we let's say optimize and appraise the oil within the Garif reservoirs, because in many cases we miss the oil. And also one of the main problems within the Garif reservoirs is the fact you have something called paleosols. Okay, so all this old soil that was depositing on the banks of these channel systems, they can impede the let's say the flow of oil between these stories or tanks of sand, as you see here. By the way, this is called the Garif Pinnacle, and it's present in central Oman, let's say close to Mhout, center of Mhout. And you can see here sand channels stacked on top of each other, and in between them you can see a paleosol. So these paleosols, they can actually make hinder or impede the oil flow between these sand reservoirs. They can also cause compartmentalization, so they can segment the field into different parts, therefore making the development of the reservoir quite a problem. One of the things about Garif, as I said, the deeper it goes, the very low permeability and porosity becomes because of compaction, and that is more or less for almost all fields of Garif. So you can see when the reservoir is shallow and Garif has not gone into heavy burial, so this is burial diagram over time, you will see that there is a lot of porosity, which are basically the blue colored areas here within this thin section, whereas here, when the burial is actually significant over time, you can see that permeability and porosity have been significantly reduced. Therefore, there is a huge spectrum of porosity and permeabilities in the Garif reservoir. So you can have basically permeability which is over 1 Darcy to permeability which is less than 1 millidarcy. And that obviously has a huge impact on the flow of oil within the Garif reservoirs. They can have also norm, so basically radioactive scales, and especially in central Oman. Therefore, in many cases, there needs to be caution and care to be taken while dealing with oil in the Garif. Traps, very similar to Qarn Alam, or what we call hemapods, which I introduced previously. Four-way dip closure. Okay, this is a terminology. Is when we have like a dome which is closed from the four sides. We call it four-way dip closure. However, if we have let's say a monocline or a dome from one side and then a fault on the other side, we call that normally a three-way dip closure. For instance, just for explanation, for Garif play, actually the viscosity tends to be very low, apart from few fields where viscosity goes slightly higher. But in most of the reservoirs, they have very light oil, and that's quite interesting because the oil that has been sourcing this area has gone. I'm just checking the comments very quickly. No comments. Okay, so some comments, but I will not take them for the time being. So again, it's very light oil within this area of Oman, and you see that most of the oil has been generated during the Permian time, more or less, and some 250 million years ago. Again, a lot of oil. One of the main problems in the Garif Reservoir is connectivity. So it needs better seismic imaging to see the channels. And unfortunately, it's a dilemma because for most of the Garif and Al Khalata reservoirs, we have poor seismic coverage. Therefore, we can't actually see these channel belts unless we are very lucky and have very high quality of seismic. But this has only been successful in a very few places in Oman. For most fields, we cannot see these or image these channels from seismic data. Eastern flank of Oman, a huge amount of fields in this area, just numerous number of fields. And you can see that there are really clusters of fields everywhere here. In some places, there are fields that have not been developed. In some places, you find names of prospects that actually quite funny. I remember we made an atlas long time ago when we were working in PDO, and I remember I found a prospect which was called Arnab, and next to it was, and this were old prospects. So Arnab, and next to it there was another prospect called Jazara. So somebody was even having fun with this, with naming the prospects in this area. So huge amount of structuration, tectonics in this area, mainly because of salt halocenosis or movement. And because of that, you get small hemapods or turtle-back structures that I explained last time. And within this, you have different reservoirs and different fields. This is an example, Marmul field, a huge turtle-back structure. This is a published section, so there is no problem to show it. And you can see the structure is massive, actually. This is 5 kilometers. And by the way, Marmul was actually discovered long time ago, in 1956, I think, but it wasn't possible to produce it until 1980 because the oil is heavy and technology was not supportive in the 1950s, 60s, and 70s. Okay, so again, poor imaging. You can see that seismic quality, obviously seismic quality has improved significantly lately. So if I go switch very quickly to Petroleum just to show you a seismic section from that area, not to be specific, but anyway, just to show you and get you to feel the overall feeling in that area without again mentioning name. Okay, I have Petroleum stuck. Okay, now it's coming back. Let me just choose one of the seismic surveys. Okay, so I'll choose one of the seismic section. You can see that the seismic section, if I show it in Petroleum, I'll put this 5. Clarity. You can see seismic quality is in overall very poor, but there has been recent processing that improves the seismic quality within a lot of areas in South Oman, where you can interpret things to quite good confidence, but again, it's still not very great. Okay, I think I'm closing out this. I was still in lecture 1, by the way, so sorry for being so late. Anyway, I think I'm catching up now. So again, for the oil within the eastern flank play, it tends to be very heavy. Okay, So gravity is low, whereas viscosity is high, and you can see it goes more than 1,000 in some field, like Mukhezna, for instance. That's why in Mukhezna they develop it with with steam or basically thermal development. GOR tends to be very low, and depth not that much of deep structures, but in some places you can have some deep structures as well. Most of the oil has been generated, as per this diagram. It has been reached through various times. I can see here, and the oil window covers from 2.5 to 5 kilometers, which is quite deep. Why? Because the geothermal gradient in South Oman is quite low, so it requires more burial for the oil to be matured or to expel what do you call it, oil. So what is unique about the petroleum system of Oman? There are two slides I'm covering here. And first of all, poor seismic quality in many places, small size of traps, and very complex oil accumulation. That's unlike many other places in Oman, in the world, where oil is more easy to produce, especially in the Gulf, for instance. And also we have a huge history of petroleum system that goes back to more than 500 million years ago, and that obviously adds a factor of complexity to the petroleum system of Oman. And what is important in the next 60 years, is to have smart people like yourselves to be able to produce or bring new technologies to extract oil from the ground. In many occasions in the past, we thought that oil in Oman is running out, but we always add more volume and reserves into our books, and therefore, inshallah, oil will last, and hydrocarbon overall in Oman will last for decades to come, and it will always be in demand, inshallah. So, but again, it needs very good geologists or geoscientists and engineers to do the proper work. Okay, ladies and gents, so I'll move now to the second slide package, and not many slides here, so I'll move quickly as well. We'll speak here mainly about geophysics, and in geophysics, I'm not a geophysicist, by the way, but I'll do my best to explain things. And so there are, last time I mentioned that there are different types of geologists. We have what's called the well site geologists, who will be sitting there in the rig site to identify rocks, for instance, okay, that come out as cuttings from the drilling rigs. One of his roles and responsibilities. And then we have also exploration geologists who work in exploration, and then he will be doing assessment of the plays and prospects. We will have a production geologist who will do in many cases, what do you call it, update geological models, planning wells and managing of data, whereas we have development geologists who usually extract different types of data from various sources and will make a robust geological model fit for purpose for whatever reason the model is constructed for. Then we also have, for instance, operation geologists who will follow the drilling by the rigs. There will be also, for instance, well surveillance geologists who will follow up the various surveillance or surveys that we do in these wells. And for big fields, this type of geologist is important. We have, I'm sure I'll be missing some types of geologists working in petroleum companies, but there are a big spectrum of different types of geologists. And for small companies, in many cases, one single geologist will do all of this office work, whereas they would have contracted probably a company to bring them well-site geologists to work in the rig sites. So among the geophysical data that we use in petroleum, identify petroleum system, and these are kind of old technologies, but they still implied with obviously a huge advancement in the way they work. is gravity, magnetic, which are usually airborne. So we usually use airlines to acquire this data, and seismic, whereby we use either vessels or ships to acquire seismic uh, on the offshore, whereas we use what do you call it, vibro size or trucks, basically to hammer the ground and produce signals, and then we use other tracks to record the signals, which are usually captured but by what we call geophones or the receivers. And the setup nowadays is done for normally for 3D seismic, whereby a huge amount of geophones are placed on the ground for a specific certain area that is defined by a certain company. And then all these vibro sizes and recording tracks and the whole campaign will just go there to produce that 3D seismic cube. So why we go for gravity and magnetic? Because gravity and magnetic can see things, especially deep, that seismic cannot see. So, and also they are cheap. Okay. So in many cases, when we don't know about the play or the basin, we want to have a quick idea about it. So we run gravity and magnetic. They certainly, for petroleum industry, they really significantly cheaper than seismic. It goes similar to mining when we acquire gravity and magnetic for large area, so that we avoid doing a lot of drilling, which is costly as well as hectic in terms of getting permissions. So for gravity, you will see here, for instance, sediment here is thick, whereas the basement, which is igneous rocks or metamorphic rocks, is thin. You would see that both gravity and magnetic have gone down because you have thicker sedimentary rocks compared to basement rocks. Whereas when you have only basement, hard rocks, metamorphic or igneous, you get high values of gravity and magnetic. If you have, for instance, a basement fault, you would also be able to see it. If it's a huge basement fault, you will be able to see it both from gravity and magnetic. If you have, for instance, intrusion, gravity might not see it, but the magnetic can see it, you know. So there is a reason why to have both components. In some cases, for reef, for instance, for a reef, if you have a uniform thickness of the sedimentary basin, then the magnetic will not see it. But because the reef will have lower gravity, the buildup, then you will see it in gravity, but you won't see it in magnetic. So both of them, they have here, for instance, magnetic can see the salt intrusion or salt dome, but gravity will be more conclusive here. So it's very useful. This is just an example. I'm not going to go through it now. Seismic acquisition, looking at time now, maybe you can cover a lot of that by kind of reading. It's not really complex. But here, let's just make the slides Oman specific, and especially that we have about 15 minutes left. So here, for seismic quality, it heavily depends on reflection, or what we call reflection coefficient. So the ability of rock to reflect seismic, you know. So here, for instance, in Oman, we have carbonate rocks in North Oman, whereby you get very hard rocks interbedded with soft rocks of mudstone, marls, or shale, and therefore you have big differences in reflection coefficient in the ability of the rocks to reflect seismic. Therefore, the seismic quality tends to be good. So there is what we call acoustic impedance difference in reflection coefficient is high. Therefore, you can see the rocks better. Whereas in South Oman, when you have a huge pile of clastic rocks or siliciclastic rocks put on top of each other, and that difference between these rocks in terms of reflectivity is not high, then you get poor seismic signaling or reflection of the underground. So here, for instance, if you move from strong rock where velocity is high and density is high, to poor rock where the velocity is lower and density is lower, you can see the signal reflection coefficient is basically reduced, and this would be imaged in seismic, hopefully, if this layer is thick enough to be seen by seismic data. Acquisition, I'll jump these few slides because I really want to focus on the stuff that is important for Oman and also important for you, and mainly focus on processes of seismic that are important for Oman. So anyways, when we receive the data, usually it's raw and it looks like this. So we have to do a number of processing. And by the way, processing is usually cheaper, much cheaper than acquisition. Therefore, many companies, they prefer to, what do you call it, reprocess the seismic data instead of acquiring new data. And instead of sending all this seismic crews to acquire new data, they prefer to find new technologies of reprocessing the data, therefore saving time, effort, and cost. It goes into a number of things. So anyway, eventually we get pulses, so these reflections as the seismic signal goes through the rocks. You need to do a lot of refining, a lot of removal of the waves that you don't want. Eventually, what you want is the reflection wave, which is basically, in this case, the red one, I think, is that what you are mostly, interested at. Seismic migration is to try to get the seismic back to its original, the reflection back to its original place in the underground because of dipping strata or complex geology. Sometimes you may not image on the surface the structure in the correct position. So you need to do correction, and that correction is usually done by trial processing, trial and error, kind of, until you receive the proper imaging of the subsurface where seismic looks representative of the subsurface structures without signals crossing each other as they appear on the top image. And actually, when you do that, then you have to use velocity data, and that velocity data you get it, and you use it as what's called seismic processing velocities, that you can use it for something called depth conversion. I'll get to that. Deconvolution, again, not to spend much time here, is just a process where we try to remove something from seismic data called multiples. So multiples are when seismic signal goes through a certain layer, and maybe because of the high reflection coefficient of that layer or that boundary, the seismic seismic signal or wave, when it goes into the layer, it gets reflected a number of times inside it. So the same surface in the subsurface get imaged constantly at the same thickness, and you would see the same layer being repeated maybe multiple times. So you need to be aware of that, and obviously the processing techniques nowadays remove this, and you can see the seismic in various ways. So you can see it in black and white, for instance, as wiggles. You can see it also as color index, blue, red, or black, white, red, whichever color you prefer. Many seismologists prefer this color. Others prefer this one because it's better for the eyes, and sometimes it makes things actually sharper. Synthetic seismic is actually a beautiful term. Just to make you aware of it, is synthetic seismic is, let's say, it's not a true seismic data acquired by seismic crews and so on. It's a seismic you try to create from your well data. So you have a certain well, and within it has density, and it has also velocity. So what you do here is that you multiply density by velocity, which is coming from the sonic logs. So you have this density and sonic logs, velocity and density. You multiply this to get with getting an idea about the reflection coefficient. You get representation of that reflection coefficient using certain wavelets. So you apply certain wavelets into this, and from these values you create your own seismic. It's just that you use these logs that you acquire from the well data in order for you to produce seismic data along the wellbores. So that's what we call synthetic seismic. Why do we create it? We create it because it's a very beautiful tool. If we get a successful synthetic seismic to tie with real seismic data, okay? So let me show you in Petroleum. So here I don't have a synthetic seismic, but presumably if I have a well like this and I produce within it as a synthetic seismic data like this one, for instance, I can then bring the seismic section, okay? I can bring the seismic section close to the well, and if I do this, then I can compare. So if I do that, then I can put the well tops within this well, like this. For instance, this blue color well top is for top Garif. I will be able to see which reflection within the synthetic seismic compared to the real seismic. And that would be very beautiful, because then I will be able to convince others that this reflection that I see in the seismic data is definitely for Garif, because I made a synthetic seismic and it compares beautifully with the, what do you call it? It compares beautifully with the seismic cube. So synthetic seismic is very beautiful, actually, tool if it works. Okay, back to the seismic, the, what do you call it, the slides. Well seismic, another type of seismic data whereby you actually acquire seismic within a certain well bore. How do you do this? You either put your receivers within your well bore, so a receiver which moves across the well bore, okay, and you shoot seismic on the surface, and that receiver you, what do you call it, measure the time it sees, it listens to a signal, okay. So you have a well bore, you put a certain receiver there, and then you source a seismic from top, and then you hear when did you receive that, signal on your well bore, and from there you can make time depth relationships, so you will know that the seismic wave takes this certain amount of time to be received by that receiver. And you also have knowledge about the depth of the receiver, so you know that in 1000 meters it will take seismic, for instance, 1 second to reach to my receiver. And this is very beautiful, very good, very nice. Why? Because then you can use this time depth relationship to convert seismic. Moreover, if the spacing between these receivers is small, so a few meters for instance, then you will be able to make actually a seismic wavelet across that well bore and compare it to seismic data. You can also compare it to synthetic seismic, okay? And these are very beautiful tools. If they work, then you can be very confident when you make your interpretation of the seismic data, because then you'll be able to tell which horizon is which, okay? Seismic resolution is usually very limited. So the best you would probably get is around 12 meters. Anything below that, seismic is not going to be able to see it. So if you have a fault, for instance, whereby the offset between the layers is only, let's say, 4 meters or 5 meters, it's very likely you're not going to see it. How do you measure that? You need to divide velocity by frequency by 4. Okay, so if assumingly the velocity is 3000, the frequency, which is expected for seismic data by the time they reach the level of the reservoir, is 60 hertz. Then the quality of resolution is 12 meters. You won't be normally able to reach 100 hertz frequency at the reservoir level. Therefore, and for that you will also need to have what do you call it, high velocities in order well, you need to have good velocities in order to image the seismic data. Just a comparison. Okay, this is, I'll just skip to this slide. So in this slide you can see that for a mountain like this, seismic will show you 2 signals. So it will only see this package, and then for this poor reservoir it will see negative wavelet signal, and for this strong reservoir it will see a positive signal, and it will only be able to see that. It will not see the bedding, details of bedding. How would you see that? You will see that from logs, because logs can give you 30 centimeters or 25 or 20 centimeters resolution, so you can see a lot of the bedding here, but again it's not conclusive. The outcrops are much better. Outcrops are great. What is comparable to outcrops? Core data is when you try to obtain a core from your well. That's very good, because then you can really choose to go very, very detailed into your interpretation and go as detailed as micrometer in terms of resolution. I think, okay, I'll make this, I'll explain this when I go to Petrel in a minute. So in terms of, I was going to speak, I'll leave a few slides here. So 4D seismic is actually very beautiful to speak about. Okay, let me actually use, I have 5 minutes, so I want to use them for Petrel. I will cover this part next Thursday, so day after tomorrow, inshallah, when we do lecture number 3. So if we go back to Petroleum, so when you look at seismic cube in Petroleum, you have wells, okay, I'm removing well names and so on just for confidentiality here. But if I put a seismic cube, for instance, okay, let's say this would be the size of this seismic cube. I still cannot see it. Now you can see it. So here you have a seismic cube, which is very big actually, and it covers many fields. And you can see this is now a time slice. So kind of horizontal slice on time, okay, on a certain time on the seismic. Whereas this one is vertical. So this is vertical slice, whereas this is horizontal slice. And you can see all these rounded features that you see here are most likely pods, okay, hymapods. So whenever you have a circle, it's one of the fields which is producing. There is one circle here, there is another one here, here, and so forth, okay? And obviously you can then move the seismic slice up and down to image the seismic in a good way. And then you also can have different, you can see here you have different what's called cross lines and inlines. And cross lines are the way you basically put your geophones. So one array of geophones would be, for instance, inlines, and the opposite direction of this array will be called the cross line, okay? And these inlines and cross lines, they give you ability to interpret seismic data in various directions, okay? So you can see these beautiful hymapods here, okay? And then the top formation, that is, you see a beautiful unconformity here. This unconformity is of the Naruma, and usually the Natih formation, so this red reflection and black reflection here is usually for the Natih formation, which is unconformably sitting on top of the Haima plastic and the Garif al-Khalata plastic. So what you do here is when you look at this, you can also put random lines. So not only inlines and cross lines, you can also put north, east, and southwest section. Whichever section you would like to see, you can also put a section that goes through the wall. You can also put a section that actually goes across the wall, so it doesn't go uniform, planar. It goes zigzag through various walls. So then you can actually interpret the seismic exactly on the well locations. I'll speak a bit next time about seismic interpretation. When you do seismic interpretation, you start to do picking. Okay, so you pick a certain horizon to produce a certain surface. So if I show you, for instance, now one of the interpretation, so I put Natih, for instance, interpretation, you would see that somebody here, okay, has figured out that Natih, for instance, okay, is this reflection, red reflection here, part of the Natih. So this is Natih E actually, whereas probably the top one is Natih A. Anyways, whichever it is, so here somebody has tried to pick this reflection, follow it up, okay, and produce a 3D image of the Natih. And then later on, we can take this image of the Natih to make a surface. And in that surface, you can choose how big that surface is, okay, in order for you to image it. Anyways, I'm running out of time, so only have 2 minutes left. I'll do more Petroleum promise next time, inshallah, and I'll also finish a bit about the seismic data next time we meet. Okay, ladies and gents, sorry for hopefully not trying to complicate the story. Thank you very much.